Okay, good morning everybody. Giving a little lecture from my home. Here, I'll say hi for the camera. Hi. All right, I hope that looked okay. All right, so today is the 7th of May, and we are on chapter 11. Hopefully you can see that okay. And our task is learning about electrochemistry. The first thing I'm going to talk about is combine half reactions to get the E of the cell. So this is a little bit of a review of what we've been doing before, but I know that students have trouble with this, so I'm just going to mention the reactions that are on WebAssign number 8, and this tells you that the manganese, that is an impurity in steel, can be oxidized with nitrate, nitric acid. Okay, so they give you this general reaction in words, and how do we find the E of the cell for that? E0 of the cell. Okay, we have to find the appropriate half reactions. So manganese is going to be oxidized. It's going to lose electrons, and it will be forming its ion. And here you can see manganese. It's going to go backwards on this from this table, and the E0 value for the forward reaction is minus 1.18. For the reverse reaction, it's going to be positive 1.18. So let's go ahead and write that. Mn goes to Mn2 plus 2 electrons, and that is positive 1.18. The other reaction is NO3 minus plus 4H plus 3 electrons gives you NO plus 2 H2O, and that one comes from the table as well. Right here, NO3, 4H plus, so on, 0.96. So that one is as written, and so we can keep it as 0.96. Now to combine these, we need to find the lowest factor and multiply through by that factor. So you can see 6, and that's going to be the total number of electrons transferred. So this one has to be times 3, and this one has to be times 2. Now notice that we don't do anything with the E values over here, just leave them as is, and we can combine these two reactions, getting 3 Mn plus 2 NO3 minus plus 8 H plus goes to 3 Mn2 plus 2 NO plus 4 H2O, and that gives us an E0 value of 2.14 volts. Okay, so recognizing how to find the half reactions from a given reaction that is specified. Related to this is this idea of predicting spontaneity, and the key here is finding a positive E0 value. Okay, so let's take a look at a question. Will I2 oxidize Br minus? Okay, this would be a typical exam question, and you have to look at this verb here to understand what is happening. So if something is going to get oxidized, it's going to lose electrons. If something is doing the oxidizing, it is the oxidizing agent. So let's write that reaction. I2 plus 2 Br minus goes to 2 I minus plus Br2. So we can take a look at, make sure that the electrons are flowing in the way we think they are. So 0 oxidation state minus 1 oxidation state, that is a reduction. And here we're going from minus 1 oxidation state to 0, and that is oxidation. Getting more positive and losing electrons. Okay, so now if we look at the table, we want to find those half reactions. So I2 going to I minus. That one is right there. I2, that's plus 0.54. I2 plus 2 electrons goes to 2. I minus plus 0.54. And the other one is going to be reversed on the table. So that one is over here. Br2 plus 2 electrons goes to 2 Br minus. We want the reverse of that. We want Br minus going to Br2. So we flip that one around. It's going to be minus 1.09 volts. So here we've got 2 Br minus goes to Br2 plus 2 electrons minus 1.09 volts. And so if we add those two together, I2 plus 2 Br minus goes to Br2 plus 2 I minus, and you can see that this is going to be a negative number right there. And so because of that, this reaction is not spontaneous. And the answer to the question, will I2 oxidize Br minus, is no, based on that negative value. Okay, so that kind of gets us caught up to where we were last week. Next topic is called the Nernst equation. Okay, so this is for non-standard conditions and finding the E value of the cell. Okay, so E without the zero, find E of the cell for non-standard conditions. So essentially, when the reactants and products are not at 1 molar concentration, which happens as soon as the wires are connected and the electrons begin to flow. Okay, so the analogy is to the delta G reaction that we were given in the last chapter, and that one is delta G equals delta G0 plus RT ln of Q. The Nernst equation is E equals E0 minus RT over NF ln Q. Okay, where R is the gas constant, temperature, moles of electrons, and the Faraday constant, which we discussed already. The nice thing about this unit is all of our problems are going to be solved at 298 K. So the Nernst equation takes on a different form, and it looks like this: 0.0591 over moles of electrons times log base 10 of Q. Okay, so that's the equation that we're going to be using, the Nernst equation. And so let's look at an example here of how that might be useful. Okay, so we're going to look at the Cu2 plus and Zn2 plus cell. And we have our two half reactions, Cu2 plus 2 electrons goes to Cu, 0.34 volts. That one is combined with a Zn, going to Zn2 plus 2 electrons, 0.76 volts. And we can combine that to make Cu2 plus zinc goes to zinc 2 plus Cu, giving us 1.10 volts. Okay, so the Nernst equation for this reaction is E equals 1.10 volts, that is E0, minus 0.0591 over 2. This is the moles of electrons, and hopefully you can see that from this reaction, 2 moles of electrons, 2 moles of electrons, Log, and the expression for Q is products over reactants. And so the product here is Zn 2+, and the reactant is Cu 2+. Okay, and so think about the reaction. As soon as the reaction begins, the concentration of Zn2+ goes up, and the concentration of Cu2+ goes down. Reactants are going to get lost, and products are going to be formed. And so what does this do to the value of Q and the log of Q? So Zn2+ is getting larger, and Cu2+ is getting smaller. Well, you can see that the ratio is becoming greater than 1, Q greater than 1, so log of Q greater than 0, and E then equals 1.10, positive number, minus a positive number. Okay, so that's number's going to be getting smaller. E is going to get smaller. So E approaches 0 as the reaction takes place. And this is why batteries discharge and eventually drain down, because the reactants are getting used up and the products are getting formed. And because Q is progressively becoming more positive, that is subtracting from E0, making E eventually approaching 0, and equilibrium will be reached when E equals 0. So that's the next topic here, is let's relate this to the equilibrium condition. Okay, so at equilibrium, then remember that we had delta G0 equals minus RT ln of K, and this was because when Q equals K and delta G equals delta G0, delta G equals delta G0 plus RT ln of Q, that becomes delta G0 equals minus RT ln of K. All right, now with the Nernst equation, we're going to have Q equals K and E equals E0, so we have ln of KEQ equals number of moles of electrons times the Faraday's constant times the E0 value over RT, and at 298K we have log 10 of K EQ equals the number of moles of electrons times the E0 value divided by 0.0591. And that is our equation relating equilibrium constant with the E of the cell. Okay, so here is some example problems. I'm going to work one for the Nernst equation, where we'll change the concentrations of reactants and products and calculate the E of the cell. And the next one will be to calculate the equilibrium constant based on the E of the cell. Okay, So the first problem here is from the lecture notes, the slides, which says calculate the potential of a cell based on the half reactions. This one here, vanadium oxide, and this one here, the zinc. Okay, when the following concentrations are present in the cell. So here's our initial concentrations. This is going to allow us to calculate Q, and these half reactions will allow us to calculate E0 of the cell. And once we have Q and E0, then we can calculate E. Okay, so we have given two half reactions. One of them is VO2 plus 2 H plus an electron goes to VO2 plus H2O, and the E0 value is 1.0. And the second one is Zn2 plus 2 electrons gives you Zn, and that's minus 0.76. So we have to combine those two in order to get a positive E value, E of the cell, and you can see that this one, lower one, is going to need to be flipped over because that's going to be the oxidation. So that is going to give us VO2 plus 2 H plus an electron. You can also see that the top reaction needs to be multiplied by 2. Okay, so let's just go ahead and do that. That's going to be 4, and that's going to be 2 electrons. Gives us 2 VO2 plus H2O. Once again, I don't multiply the E value by that factor of 2. Go ahead and flip the bottom one. Zn goes to Zn2 plus 2 electrons. That one is positive 0.76. And we can combine these two now to get 2 VO2 plus Zn plus 4 H plus, electrons cancel, goes to 2 VO2 plus 2 H2O plus Zn2 plus. And the E0 value equals 1.76. Now we're given the starting concentrations for these ions. This is 2 molar. Zinc is a solid, so we don't consider that one. And hydrogen ion is 0.5 molar. VO2 plus is 0.01 molar. We don't consider water because it's a liquid, and Zn2 plus is 0.1 molar. Okay, and so now we can put this into our Nernst equation. Okay, so we have E equals E0 minus 0.0591 over N log of Q. E equals 1.76 minus 0.0591 over the number of electrons transferred, and that is 2. And the log of the products, which is 0.01 squared. Okay, so you can see we've got 0.01, and we're going to have 0.1. And this is divided by 2 squared and 0.5 to the 4th power. Okay, and that is because the hydrogen ion has a 4 in front of it, so that's to the 4th power. Okay, and so then we evaluate that, and we get 1.89. Okay, so you can see that E is greater than E0 because the products are at low concentration. And if there's not that many products, then the reaction is going to be favored to go forward. Okay, the last example problem is equilibrium constant problem. And this one says, calculate the equilibrium constant for this reaction. So let's go ahead and do that one. Calculate the KEQ for NO3 minus plus 4H plus 3 Ag. There's an equilibrium with NO plus 2 H2O plus 3 Ag plus. Okay, now we have to find our E of the cell because the equation is log of KEQ equals N E0 over 0.591. Finding that E of the cell, we need to find the half reactions. So we've got the nitrogen half reaction and the silver half reaction. We go ahead and look on the table. The nitrate one we have seen before, and that is as written, so that is 0.96. And the silver is the reverse of what is shown on the table, and that one is right here. You can see Ag plus goes to Ag plus 0.8. This one is Ag goes to Ag plus, so that is going to be minus 0.80. And so the E0 value for this reaction is going to be 0.96 minus 0.8, 0.16 volts. N equals 3 electrons. Every silver is going to transfer 1 electron, and there's 3 of them. Okay, so then we get log of KEQ equals 3 times 0.16 over 0.0591, and this equals 8.122. Now to isolate KEQ, we want to raise 10 to the power of 8.122. That is the inverse of log, and then equals 1.32 times 10 to the 8th. You can see a very large number because the E0 value is positive. Okay, so next time I will talk about concentration cells and electrolysis and KSP. Those are our final topics for Chapter 11. Have a great day, everyone.